Hey everybody, Mr. Brooks here again. So today we're going to cover section 4.6, dealing with complex eigenvalues. So the previous one we dealt with just real eigenvalues for our first order systems, and so this is what we're going to be dealing with today. So again, our focus is on the complex in this sense. So our first example here is find the eigenvalues and eigenvectors for the matrix A that corresponds to the following system, where A is equal to the matrix 1, 1, negative 1, 1. All right, like before for our solution, we need to first find, in order to find these eigenvalues, the determinant of A minus lambda I. So this would equal the determinant of the matrix 1 minus lambda 1, negative 1, and 1 minus lambda. All right, so when we multiply these, we're going to get 1 minus lambda, the quantity squared. Negative 1 times 1 is negative 1, and then we're going to minus that, so we're going to get plus 1. And we want this to equal 0. All right, so if we subtract the 1 over, we're going to get 1 minus lambda, the quantity squared, is equal to negative 1. I take the square root of both sides, so I get 1 minus lambda is equal to plus or minus I. And therefore, if lambda is equal to 1 plus or minus I. All right, so let's look what happens in our when we find our eigenvectors with these. Okay, so let's look at lambda 1, which is equal to, we'll go 1 plus I, and we'll say lambda 2, I'm going to do that in blue to make a color difference. So lambda 2 is equal to 1 minus I. All right, so for the red one, if we plug in 1 plus I in for lambda, we're going to get the following matrix of negative I, 1, negative 1, negative I. And we're going to multiply that by our vector x1, x2. And this is equal to 0, 0. All right. Well, if we look at this, they look very similar. So we got negative I and 1 and negative 1, negative I. And in fact, if we notice here, that row 2 is just a multiple of row 1. And in fact, this case, it's a multiple of negative I. All right. So if that's the case, then this is equivalent to the following matrix of negative I, 1, 0, 0, still multiplying by our vector here of x1, x2, which is equal to 0, 0. All right. Well, when we look at this and we solve it, so we multiply this row times this column, so we're going to get negative I, x1, plus x2 is equal to 0. So therefore, x2 is equal to I, x1. So that means our vector for this, our eigenvector, is of the form x1, x2, and we could say that, so x1, x2. And another way that we could state that is x1 and I, x1. So that means for any value of x1, we can find our eigenvalue. So that means I can plug in here x1 is equal to 1 and get 1i as my non-trivial eigenvector. All right, same process up here. It's in blue again. So if I plug in 1 minus I into our matrix, we're going to get the following. We're going to get I, 1, negative 1, I, and we're going to get x1, x2 is equal to the 0 vector here. And looking at this again, there's again a relationship between the first row and the second row, and in fact row 2 is equal to I, row 1. So our equivalent matrix then is I1, 0, 0, x1, x2 is equal to the 0 vector. Well, solving this, we get ix1 plus x2 is equal to 0. So therefore, x2 is equal to negative ix1. And like before, x2, our eigenvector for this one, is x1, x2. And a way we can write that again is x1, negative ix1. And to get a non-trivial value, we let x equal some easy number here. So we're going to let it equal 1, and we're going to get negative I. Notice the relationship of x1 and x2 to the eigenvectors. So the eigenvalues, notice that they have our conjugate pair. Well, in fact, x1 and x2 also are conjugate pairs in this case. So that leads us to our first note here. Note, for polynomials with real coefficients, complex roots always show up in conjugate pairs. This generalizes to matrices with real valued entries, where complex eigenvalues always occur in conjugate pairs, where the only difference between the two is a sign of change of the complex value associated with it. And two, the more important one here, is if lambda is a complex eigenvalue with corresponding eigenvalue or eigenvector x, trying to keep it bolded there, then x bar is an eigenvector for eigenvalue lambda bar, where the bar is the complex conjugate of lambda. Likewise, x bar is the complex conjugate of the eigenvector x. So for our example that we had, just to give it, we found out lambda is equal to 1 plus I. Its conjugate pair is 1 minus I. So x here we found out was 1I. Therefore, x bar is equal to 1 negative I. So that's how these are working. So notice the only difference between the two is they're the complex conjugates of each other. All right. So the bad thing is if we have all these i's, there's an issue. All of our functions that we're building here, especially if we're dealing with real world scenarios, there is an issue with this because we're dealing with real valued functions, not complex functions. So how to convert a complex valued solution into a real valued one? Well, like before in chapter 3, we saw how we could convert those principles or those functions where we get a complex value into real valued functions. And we're going to extend that idea into systems of linear equations. All right, so again, complex valued eigenvalues and eigenvectors will always give solutions that are also complex valued. However, the systems of equations are written for real-world applications, and real-world objects do not exhibit complex valued behavior. So therefore, we must be able to convert to these real values. All right, so like before, if we were looking at our particular eigenpair that we had here, so let's compute a solution that corresponds to lambda 1 was equal to 1 plus I with eigenvector x1 is equal to 1I. All right, so recall our solutions are going to be of the form E lambda t times our vector. All right, so for us, we get e to the 1 plus I t times our vector of 1I. So how can we convert that? So this is where Theorem 4.7 is going to come into play. So 4.7 says let y sub t be a solution for the first order system. Y prime is equal to ay, where t is on the any value in the real axis, so from negative infinity to infinity, where A is an n by n matrix. Okay, so if y sub t is equal to ut plus iv sub t, so notice here that we're introducing new vector functions here, is a complex solution where u of t and v of t are each real valued solutions of y prime a sub y. So this is the cool part, is just like before in chapter 3, where we got to use these real valued pieces, that's what we're going to be using as our solutions as well. So we need to be able to rewrite. Well, if we remember from the previous chapter, we used Euler's formula. So from Euler's formula, we can rewrite e to the 1 plus I of t is equal to e to the t, e to the it. Again, just this is just basic properties of exponents and where the bases are the same. All right. Well, rewriting our complex value here of it or I theta, we get e to the t times cosine of t plus I sine of t. Again, this is our basic property or basic formula from Euler's formula. And again, just writing this out, we get e to the t cosine of t plus I e to the t sine of t. Okay. Thus, we can rewrite our solution as the following. y1 of t is equal to, and here I'm just going to put y of t. There's a reason for that here in a second. E to the t cosine of t plus I e to the t sine of t times our vector of 1I. So when we multiply that, we are going to get a new vector function here, because this is just a function multiplying it, so we just treat it as a constant multiple in that case. We're going to get e to the t cosine of t plus I e to the t sine of t. And then when we multiply it to our second value, we're going to get I e to the t cosine of t. Well, those i's, when I squared, we're going to get negative 1. So negative e to the t sine of t. Which, if we rewrite, again, finding that u of t and v of t, so the new vectors here, we're going to get the form, well, everything that's real, so nothing that has an I part in it. So in this first group, we have e to the t cosine of t. And in the bottom here, our real part of this is negative e to the t sine of t plus I times e to the t sine of t, coming from this part here, and then e to the t cosine of t, coming from here. All right, so this is our u of t, this is our v of t. All righty. So by Theorem 4.7, where u of t is equal to, and I'm going to again rewrite this, and v of t was equal to e to the t sine of t, e to the t cosine of t. These guys are solutions. Of our original equation. All right. Well, we could verify this if we plug them directly in. So if we take the derivative of u of t, we're going to get a product rule here. First times the derivative of the second, second times the derivative of the first, and whatnot. And we could compare it by multiplying e to the t cosine of t, negative e to the t sine of t, by our matrix up here. Again, as a reminder of which one this is going with, of 1, 1, negative 1, 1. And that would be the same result. So we can verify this again by direct substitution. Okay. Now, the big thing here is we need to check, because if they're solutions, that's great, but we need to check if they form a fundamental set. Okay. Well, that means we're going to take the Wronskian of uv. So when we do that, we're going to get e to the t cosine of t, e to the t sine of t, negative e to the t sine of t, e to the t cosine of t. All right, we multiply by the diagonals and subtract. So we're going to get e to the 2t cosine squared of t minus a negative, so plus e to the 2t sine of squared of t. All right, well, if we factor out the e to the 2t, cosine squared plus sine squared is equal to 1. So this is equal to e to the 2t, which is never equal to 0. Therefore, our general solution is y of t is equal to c1 u of t plus c2 v of t, which we can write as c1 times u of t, which was e to the t cosine of t, negative e to the t sine of t, plus c2 v of e to the t sine of t, e to the t cosine of t. All right, and this is our general solution. Moving on. So that's the cool thing. And also, if we would have a similar result if we used y2, where we had lambda is equal to 1 minus I, and we had 1 negative I, we would get a similar result coming from this. And remember, back in the previous sections, we talked about how you can multiply your original. So in our case, our original solution set, if we were to look at it, would be, and I'm going to go up here for a second. So our set, if we said y1 of t is equal to e to the 1 plus I of t times 1i, and y2 of t is equal to e to the 1 minus I of t, 1 negative I. Once we verified this, we found that these guys are linearly independent because they have different eigenvalues, so this is great. So everything's working out well for us. So we could say then our psi is of the form e to the 1 plus I of t, I e to the 1 plus I of t, and then e to the 1 minus I of t, negative I e to the 1 minus I of t. Now from Theorem 4.5, which was saying we could multiply this by some constant coefficient matrix and get out this new psi. Okay, there is a way to multiply it, and if you look in your book, there is a it deals with half values when you're multiplying it, but there is a way to get there. So from Theorem 4.5, we know that our sets or fundamental sets are not always unique when it comes to these matrices. So this is a solution set for us. And if we multiply again by the constant coefficient matrix, there is a way to get back to the originals that we had just written. So that's the really cool thing about this. So that's why I didn't go ahead and look at this for the second lambda value, because we would get a similar solution set in the end. All right, so that's the good thing, is we have less work to do with it, but we still have to convert from complex functions into real valued functions in that case. All right, so moving on, let's look at a 3 by 3 here. So find the general solution for the following system: 2, 0, negative 4, 0, 1, 0, 2, 0, negative 2. So first of all, like before, I'm going to find the determinant of a minus I lambda, or lambda I. So again, we're just subtracting along. I gave away what we were doing. So when we do this, I'm going to get 2 minus lambda times 1 minus lambda times negative 2 minus lambda minus 0 plus negative 4 times its determinant, which was negative 2, 1 minus lambda. All right. So again, the 0 here multiplied by its minor, that's going to go to 0, so I did not include that in our calculation. One, to save time, and two, I think you guys are at a high enough level that you don't have to worry about that piece. All right, so multiplying things out, we're going to get 2 minus lambda times lambda squared plus lambda minus 2 plus 8 minus 8 lambda. And then multiplying things in and combining like terms, we're going to get negative lambda cubed plus lambda squared minus 4 lambda plus 4. Nice thing about this is I can use factoring by grouping for this. And so I'm going to group the first two terms, group the second two terms together, and I'm going to factor out a negative lambda squared, which is going to give me lambda minus 1 minus 4 times lambda minus 1. So that means we have lambda minus 1. I'm going to bring that negative out front, and lambda squared plus 4. So this is equal to 0. So either lambda is equal to 1 or lambda is equal to plus or minus 2i. So the nice thing is we really only have to work with 2i in this particular case to deal with the other two eigenvectors to get there. So that's the nice thing about this one, but I will show the work from all three just to have that in there so you can see what's done with that. All right, so lambda 1 is equal to 1, so when we plug it in, we are going to get the following matrix: 1, 0, negative 4, 0, 0, 0, so that's nice, and 2, 0, negative 3. We're going to multiply it by our eigenvector here of x1, x2, x3, and it's set all equal to 0. So doing some row operations on this guy, I am going to do row 3 minus 2 row 1. That's going to be leave me 1, 0, negative 4, 0, 0, 0, and then 0, 0, 5. We'll worry about that in a second. And then go ahead and reduce this one down 1/5 row 3. So we got 1, 0, negative 4, 0, 0, 0, and then 0, 0, 1. All right. So then we're going to multiply that by x1, x2, x3. And again, we want this to equal 0, 0, 0. All right, real quickly, we get x1 minus 4x3 is equal to 0, we get x2 can actually be any value, provided that we don't have a non-trivial case of 0, 0, 0. And then x3, since we have this 1 here, x3 has to equal 0 in this case, which implies that x1 also has to equal 0. So therefore, x1 is equal to 0, x2, 0. So choosing a non-trivial value, I'm going to just choose 1 here, which gives us a nice clean value to work with. So we get x1 is equal to 0, 1, 0. So that's our first eigenvector. All right. Moving along. Let's deal with lambda 2 is equal to 2i. And we'll do this one in green, just that way it's a separate color for this. So if I plug in 2i into my matrix, I'm going to get 2 minus 2i, 0, negative 4, 0, 1 minus 2i, 0, and then 2, 0, negative 2 minus 2i, times x1, x2, x3 is equal to 0, 0, 0. All right. Again, being careful of what you do here, I want to make sure that you're technically supposed to set up an augmented matrix, but since we're set equal to the 0 vector here, I can do all of these row reductions on the left-hand side without having to worry about implications on here. The only thing I don't do is just make sure don't switch your rows for this case, because then you'd have to change up what x1, x2, and x3 are. So just be careful on that part. Actually, you don't have to do that. Never mind. So just be careful when you're doing these row operations, making sure that if you are set to the 0, you can truncate this down to look at just the 3 by 3 for that. So here's a couple of things I am going to do. I'm going to take 1/2 row 1 and 1/2 row 2, leaving me 1 minus I, 0, negative 2, 0, 1, negative 2i, 0, 1, 0, negative 1 minus I. Then I'm going to do row 1 plus I row 3. So that leaves me a 1 up in top. That's what I'm trying to do here. And again, I didn't mess with anything on the bottom 2 rows. So here I'm just going to get a 1, a 0, and in this case, a negative 1, negative I. All right. Again, being careful of your multiplying by I, because I squared is negative 1, and so that's where you do have to be careful on these. The next step I did is I did row 3 minus row 1 to go ahead and get this to 0 here, and this is going to simplify a lot of things for us. So we're going to get 1, 0, negative 1 minus I, 0, 1 minus 2i, 0, and then 0, 0, 0. All right. So that means when we write this out, I now get 1, 0, negative 1, negative I, 0, 1 minus 2i, 0, then 0, 0, 0, times our eigenvector once we solve for it. All right, so our findings here is x1 minus 1 plus I, x3 is equal to 0. 1 minus 2i times x2 is equal to 0, and x3 can be any value. All right. Well, in this case, this implies that x2 has to equal 0. Okay? And this means x1 is equal to 1 plus I, x3. So, x2 is equal to 1 plus I, 0, 1. Because if we let x3 equal 1, then we're going to get 1 plus I. All right? So you can show the same amount of work, but since lambda 3 is equal to negative 2i, which is equal to the complex conjugate of 2, again, I'm using those properties that we had from before, then x3 is equal to the complex conjugate of x2, where we get 1 minus I, 0, 1. That's the only thing that changes is the complex number becomes the conjugate. All right. Well, again, that's unnecessary work because once I have one of these eigenvalues, I can then use that to find the u and the v from using Theorem 4.7. So that's where I'm going to go from there. All right. So again, on our findings, we found that lambda 1 was equal to 1, x1 was equal to 0, 1, 0. So that means y1 of t is equal to e to the t times 0, 1, 0. Or another way to write that is 0 e to the t 0. Okay, lambda, which was equal to 2i, and its x, I'm going to put a subscript to 2 on here, was 1 plus I, 0, 1, which means y2 of t is equal to e to the 2i of t times 1 plus I, 0, 1. Well, using Euler's formula, I'm going to rewrite this. So I'm going to get cosine of 2t plus I sine of 2t times our eigenvector of 1 plus I, 0, 1. All right. When I multiply this out, I'm going to get the following form. Okay. Again, we're going to have to FOIL these guys out, but that's okay because we're going to get cosine of 2t plus I cosine of 2t plus I sine of 2t minus sine of 2t, because I times I is negative 1, so there's where that negative sine of 2t is coming from. 0, and then cosine of 2t plus I sine of 2t. All right, rewriting this for its real and imaginary parts, we're going to get our real parts were cosine of 2t and minus sine of 2t, 0, and then cosine of 2t plus I times the imaginary parts, which was cosine of 2t plus sine of 2t. Again, adding these guys together and factoring out the I. 0, and then sine of 2t. And this is our u, and this is our v. And by Theorem 4.7, we can say that psi is equal to 0 e to the t 0. So this is our first eigenvalue that we came up with, or eigenpair, and then found out the solution. Cosine of 2t minus sine of 2t, 0 cosine of 2t, and then cosine of 2t plus sine of 2t, 0 sine of 2t. And using Abel's theorem, we can find the determinant at 0 to see if this forms a fundamental set. We're going to get 0, 1, 1, 1, 0, 0, 0, 1, 0. And we multiply the determinant, we're going to get 0 minus 1 times 0 plus 1 times 1. So in the end, this becomes positive 1, which is not equal to 0. Therefore, this forms a fundamental set. Therefore, our general solution is of the form y of t is equal to 0 e to the t 0 cosine of 2t minus sine of 2t, 0 cosine of 2t, and then cosine of 2t plus sine of 2t, 0 sine of 2t, times our C1, C2, and C3. And that's all we have to do. So the last part of this one is going back talking about phase planes and their trajectories. So last time we talked more specifically about building the vector field that it was in, or the phase plane direction field. So here we're going to look at the trajectories, which is actually looking at the specific solution and mapping it out. So this is going to be very similar to chapter 10.1 from Calc 2. So if you've got your book, look back at that. It's how to draw or graph using parametric equations, because t is going to be our parametric equation in this case, where y1 is the x-axis and y2 is the y-axis for that case. So again, here just going to go over example of these guys, because it's not that bad, especially when you have a initial value problem. But here it's going to be okay. So sketch the phase plane trajectory for the following system, where y1 prime is equal to y2 and y2 prime is equal to negative 4 y1, with the initial value where t is equal to 0, y is equal to 1 and 0. All right, so our a here in this case would equal 0, 1, negative 4, 0. All right, and I'm going to go ahead and give you its eigenpairs, which you guys can find. But we only really have to look at the following. So we get 2i, which is the first eigenvalue, and its pair, or eigenvector, which is 1, 2i. And the other is negative 2i, so again, complex pairs here, and 1 minus 2i. All right. Again, I'm going to look at this first one because that's going to give me all I need for this particular trajectory for this case. So we need a solution. So first of all, our y of t is going to equal e to the 2it times our vector of 1, 2i. So I'm going to rewrite this as cosine of 2t plus I sine of 2t times 1, 2i. So this is going to give us cosine of 2t plus I sine of 2t, so nothing changed with that first one. And then I'm going to get 2i cosine of 2t minus 2 sine of 2t. And then rewriting this in its real and imaginary parts, we're going to get cosine of 2t negative 2 sine of 2t plus I times sine of 2t and 2 cosine of 2t. So this is our u, this is our v. Knowing that they're solutions, we say y of t is now specifically c1 times cosine of 2t negative 2 sine of 2t plus c2 times sine of 2t, 2 cosine of 2t. And we had y of 0 is equal to 1, 0. So we rewrite this. Cosine of 2t, sine of 2t, negative 2 sine of 2t, 2 cosine of 2t, times C1, C2 is equal to 1, 0. All right. So plugging in 0 for t here, I kind of jumped the gun a little bit, but plugging 1 in for 0, we are going to get the following matrix. Sorry, plugging in 0 for t, we're going to get 1, 0, 0, 2, multiplied by C1, C2, which is equal to 1, 0. All right, so this means C1 is equal to 1, and 2C2 is equal to 0, which implies that C2 is equal to 0. All right, well, if that's the case, then our specific solution, y of t, is just cosine of 2t negative 2 sine of 2t. All right, so moving a little bit further, that means y1 of t is equal to cosine of 2t, and y2 of t is equal to negative 2 sine of 2t. So this is going to help us with our graphing. Cheating just a little bit here. All right, again, since we're dealing with this is y1 and this is y2, recall from chapter 10.1 or section 10.1 from Calc 2, so if you need to go back to your notes or look back in your book, do that. We're going to do this when t is increasing, okay? The nice thing is these are periodic functions, so at some point, since we have 2t here, every pi that we're going to get back to our original values. So we are going to get some sort of closed loop here. And in fact, going for specific values of t, we can also figure out the orientation for this as well. So I'm being very selective because these are really nice values of t. All right. And we're going to look at the value of y1 and y2. So when I plug in 0, I'm going to get 1, 0. When I plug in pi fourths, I'm going to get pi halves there. So it means I get 0, negative 2. I'm going to get negative 1, 0. I'm going to get 0, 2, and 1, 0. So my suggestion is when you do have a change of your period for this, to truncate your values because you might miss the orientation for these trajectories. So be very careful about that. So I'm going to go ahead and plot my points in green. So we've got 1, 0. We get 0, negative 2. We get 0, negative 1, 0. And then we get 0, 2. And then we get back to 1, 0. So if we look at this, we start here. And we rise up. And this is what our trajectory looks like for these specific values. So if we had other values of C1 and C2, we'd still get a ellipse that occurs. And in fact, if we want to go a little bit further here, recall when you're trying to draw these from section 10.1, we used a way to eliminate. So cosine squared of theta is plus sine squared of theta is equal to 1. So I'm going to kind of rewrite this to show you why it's an ellipse. So here, y1 was equal to cosine of 2t. y2 was equal to negative 2 sine of 2t, which if I rewrite that to get it to sine by itself, y sub 2 over negative 2 is equal to sine of 2t. And when I plug these values in, I'm going to get y1 squared plus y2 squared over 4 is equal to 1. And this since we are divided by 4, causes it to be an ellipse instead of a circle. So this is why we get this graph over here. So that's all you have to do for this. So when you have a specific one, you can plug in, you've got just a set of t values that you need to plug in to kind of get orientation and which direction that these guys are going. If you had a general solution, you can choose values of C1 and C2, and you can choose C1 to be 0 or C2 to be 0 to help things out. And in fact, if you look at the book, they go a different route and show you that all of them are actually going to be ellipses because they choose C1 and C2 to be r cosine of alpha and r sine of alpha, which gets everything reduced down to just a sine and a cosine for y1 and y2. So that's a way to map these guys out. All right, that's it for section 4.6. Next is going to be 4.7, dealing with what happens when we have repeated values. And then we have a very short section for 4.9, which is dealing with numerical methods. We are only going to focus on Euler's method for it. So Euler's popping up a lot these days, but it's really pretty much exactly the same as when we dealt with section 210 with Euler's method for scalar linear equations for that part. Y'all have a wonderful day.